What's up guys, I have a great video about the Fibonacci sequence. This is not the first time that I've done the Fibonacci numbers before, so if you want to check my one on graph colorings, hit that button in the corner. So today we're going to be talking about a closed form for the Fibonacci sequence. So what is the Fibonacci sequence? So the Fibonacci sequence is a really famous sequence that starts with 0 and 1, and you generate the rest of the sequence of integers by adding the previous two terms together to get the next term. So starting from 0 and 1, we get 0 plus 1, which is 1, then 2, then 3, then 5, 8, 13. It's a very famous sequence, and there is a closed form for it. The closed form is pretty contrived. It's 1 over the square root of 5 times the quantity of 1 plus the square root of 5 divided by 2 to the nth minus 1 minus square root of 5 over 2 to the nth. This represents the nth term of the Fibonacci sequence. Now, if this seems confusing, it did seem to me. The way that they usually solve it is through partial fraction decomposition and generating functions, but it doesn't reveal too much. I like to take a little bit of a slower approach. Let's analyze what's going on in this closed form. Now notice here we have the difference of two geometric sequences, one with this common ratio and the other with this common ratio. Why is this the sum of two geometric sequences? In order to do that, we need to expand our search to a more general question. Instead of just searching for the closed form for the Fibonacci sequence, let's consider what sequences satisfy the Fibonacci recurrence. And I'll refer to this as the recurrence that specifies a sequence for which each term is the sum of the previous two terms. Clearly, we already know that the Fibonacci sequence satisfies this. 0, 1, 1, 2, 3, 5, 8, and so on. Another sequence that satisfies it is we can take the Fibonacci sequence and multiply it by 2. Doing this, we get 0, 2, 2, 4, 6, 10, 16, and so on. Clearly, scaling a sequence that we previously had will result in a new sequence that satisfies the Fibonacci recurrence. What else can we do? We can also just generate an entirely new sequence. I'll use a famous sequence called the Lucas numbers. The Lucas numbers starts with 2 and 1 and follows the Fibonacci recurrence. So it would follow by 3, 4, 7, 11, and 18. But we can also do one more thing. Let's add the Fibonacci sequence and the Lucas numbers together. Doing this value-wise, we get a sequence of 0 plus 2, 1 plus 1, 1 plus 3, 2 plus 4, 3 plus 7, 5 plus 11, and 8 plus 18. Notice that this new sequence is actually satisfying the Fibonacci recurrence 2, 2, 4, 6, 10, and so on. So from this, we'll notice two things. Notice we can generate sequences that satisfy the Fibonacci relation by 1, dilating a previous sequence we already know satisfy the Fibonacci recurrence, or 2, by adding two sequences that we know satisfy the Fibonacci recurrence. So notice that in our closed form, we actually do have dilation and addition. We have the dilation and addition of two geometric sequences. So we'll move on to the second part of our investigation. What geometric sequences satisfy the Fibonacci recurrence? First, we need to know what a geometric sequence is. A geometric sequence is a sequence of numbers that starts with some starting number a, and to get the next number, you multiply by common ratio r. So the second term would be ar, the third term would be ar squared, the fourth ar cubed, and so on. Now, if I want to satisfy the Fibonacci recurrence, I need to make sure that each term is the sum of the previous two terms. This means that I'll have to make sure that ar to the n plus 2 is equal to ar to the n plus 1 plus ar to the nth. Factoring this further, we'll find that ar to the nth times r squared minus r minus 1 has to be equal to 0. I'm not interested in trivial sequences. If a is equal to 0, that means the entire sequence is just 0. If r is equal to 0, that means that everything except the first term might be just 0. I'm not interested in such trivial sequences. Assuming that ar to the n is not equal to 0, we know that r squared minus r minus 1 is equal to 0. This gives us a quadratic equation for which if r satisfies, we know that that geometric sequence will satisfy the Fibonacci recurrence. So let's just use the quadratic formula and figure out what that is. Simply, it's that r is equal to 1 plus or minus the square root of 5 divided by 2. And from here, we can see exactly how we got r in the first place. But yeah, so now we have two sequences. I'll call the first one phi1 and the second one phi2. So now we have two sequences, phi1 and phi2, which satisfy the Fibonacci relation. Now we'll move on to our third area of investigation. Now we will find the specific sequence that satisfies the Fibonacci recurrence and the initial conditions on the Fibonacci sequence. That is, the first two terms are 0 and 1. Recall from our first part that we know that we can dilate and add two sequences that satisfy FR to obtain a new sequence that satisfies the Fibonacci recurrence. So we might be inclined to say that the Fibonacci sequence can be represented as a dilation and addition of phi1 and phi2 in some manner. Let's try to do that. So we'll suppose that our Fibonacci sequence, let's say f, can be represented as the sum of these two sequences scaled by a and b, where a and b are real numbers. Now from our first part, we know that the right-hand side satisfies the Fibonacci recurrence. All we need to do is make sure it satisfies the initial conditions. First thing is that this implies that the nth term of this sequence is a times 1 plus the square root of 5 over 2 to the nth plus b times 1 minus square root of 5 over 2 to the nth. Now to make sure this satisfies the Fibonacci initial conditions, we know that f0 must be equal to 0 and that f1 must be equal to 1. What's f0? According to this formula, f0 should be a times 1 plus b. And according to the formula, f1 should be equal to a times the golden ratio plus b times the other term. Now this is simply a matter of solving a system of equations, a very simple one at that. To do that, we'll separate the rational and irrational parts in the second equation. We'll get 1 is equal to 1/2 times a plus b plus square root of 5 divided by 2 times a plus b minus 2b. Notice that we do know that a plus b is just 0, so we can simply cancel any a plus b we see in the second equation to 0. Therefore, we know that 1 is equal to the square root, the negative square root 5 times b. This implies that b is equal to negative 1 over the square root of 5. And because a plus b must be 0, a is the additive inverse, that is positive square root 1 divided by 5. Now all we need to do is substitute a and b back into the formula for which a phi1 plus b phi2 gave us. We get, which is simply, and this is precisely the closed form that we started with. So the only question left is, why did this all work? So we're going to slow down right now and talk about vectors. We'll recall from high school that vectors are things with direction and magnitude. The traditional vectors we deal with are of the form, x, y. They'll have an x coordinate and a y coordinate. They have this direction and they have this magnitude. More importantly, vectors act as mathematical objects which you can dilate and add together. So for example, I could dilate this vector xy by 1/2 to get this smaller vector, or I could add these two vectors together to get a resultant vector. You can dilate and add vectors together. The important thing about vectors is that they can form a vector space. For example, the set of all vectors in the plane is known as r squared. And what is a vector space? A vector space has one, I won't go into too much detail, but it has one important property. That property being that it is closed under dilation and addition. So clearly for any vector in r squared, you can clearly dilate it or add it to another vector in R squared and get yet another vector in R squared. The second important thing about vector spaces is the idea of a basic vector. So with basic vectors, you're supposed to be able to combine them through dilation and addition and be able to get any other vector in the vector space. Traditionally in R squared, this is done by giving you the vectors 0, 1, and 1, 0. The unit vectors along the x and y axis, clearly we can dilate these and add these together to get any other vector in the vector space. But this is not the only vectors that we could have chosen. We could have chosen any two vectors that weren't parallel to each other. And these two vectors, these two yellow vectors, could have acted as basic vectors too. You can add them and dilate them and get any other vector in the vector space. And the number of basic vectors that are required to span all vectors in the vector space is known as the dimension of the vector space. That's why we know that R squared, the plane, is considered to have two dimensions, because you need exactly two basic vectors to span the entire vector space. So what did we do with the Fibonacci sequence? What we did was just vectors. And I'm not kidding about that. Instead of considering vectors as these xy coordinates, we considered vectors as entire sequences of numbers. I guess in a way you could visualize these vectors as points in an infinitely dimensioned Euclidean space, but you don't have to, because we have the two important properties of a vectors. The two important properties is we can dilate them. We can still dilate them. We can dilate sequences, multiply it by some constant a, and we can add them to still generate new sequences. Okay, and how about a vector space? What vector space were we looking at? Now, we could look at the set of all sequences that we could possibly attain ever. That would be a perfectly fine vector space. That would have infinitely many dimensions because you need an infinite number of basic vectors. But for now, we'll specialize our interest in a subset of that. We consider the set S of sequences that satisfied the Fibonacci recurrence. And recall from our investigation that this set S is closed under dilation and addition of our vectors, our sequences. Dilation and addition will result in sequences that still satisfy the Fibonacci recurrence. And so it turns out that the dimension of S is 2. Consider the basic vectors S1 and S2, where S1 is a sequence generated by 0 and 1. Now that just turns out to be the Fibonacci sequence itself, and S2 is a sequence generated by 1 and then 0, which turns out to be a sort of shifted Fibonacci sequence. So how do we know that these are basic vectors? Simply consider any sequence that satisfies the Fibonacci recurrence. So consider an arbitrary sequence in S. Now, there is an easy way to represent this sequence as a dilation and combination of S1 and S2. Simply multiply S1 by X1 and multiply S2 by X0. This will result in a sequence which we know from the first two terms it must start with X0 and X1. And because both sequences must satisfy the Fibonacci recurrence, we know the next term is going to be X2 and so on. So these two sequences are equal to each other. Because we can represent any arbitrary sequence as a combination of S1 and S2, we know that these two basic vectors span the vector space S. Therefore, only two vectors are needed. The dimension is 2. Lastly, we were considering the vectors phi1 and phi2, which we know are both elements of S. These are geometric sequences. Okay, we know they're geometric sequences. The question is whether these two sequences can be basic vectors, whether they can span the vector space. Let's see if they can. We will take an arbitrary sequence in S, and we'll try to find a combination of phi1 and phi2, which is equal to that sequence. In this case, we use the same idea that the first two elements of a sequence uniquely determine the rest of the sequence because of the Fibonacci recurrence. So we know that the first term x0, it must be equal to a plus b, and that the second term must be equal to a times 1 plus the square root of 5 divided by 2 plus b times 1 minus the square root of 5 over 2. Now, you can solve this for yourself. And it turns out, we can even use matrix algebra here, but it turns out that this system is always solvable. You can always solve for a and b. Now, I'm not going to do that here, but it's pretty easy to do that, to brute force this. You can express a and b in terms of x0 and x1. And once we do that, we have now proved that any arbitrary sequence that satisfies the Fibonacci recurrence can be represented as a combination of phi1 and phi2. Therefore, phi1 and phi2 are basic vectors of S, and they span S. Because they span S, we know that there's some combination of them which will equal the Fibonacci sequence. So as I remember what we've done, we've considered the vector space of all sequences which satisfy the Fibonacci recurrence, S. We found two basic vectors, phi1 and phi2. And because they're basic vectors that span S, we know that some combination of them has to lead up to the Fibonacci sequence. And it was pretty easy to do so. And that solution, that exact solution, using these basic vectors, which were geometric sequences, that was precisely the closed form that we found. Simply that the nth Fibonacci number is equal to 1 over the square root of 5 times 1 plus the square root of 5 divided by 2 to the n minus 1 minus the square root of 5 divided by 2 to the n. So I hope you found this cool. If you did, I would highly recommend taking a look at a linear algebra course, because this is what you will be doing. And even more cool stuff than this, you could be doing this with graphs or differential equations. Thanks for watching.